Now let's get started. We are actually recording the full meeting today, not starting a couple minutes in like we normally manage to do. We're delighted today to have two cosmology-focused talks. But before we do that, Anna volunteered to say a couple words about something really exciting, which is happening today, which is the Gaia Early Data Release 3.
Yes, actually, Gwen, can you stop sharing? I
Sure.
remembered I wanted to show something. Yeah, I figured that it would be better if I, instead of just talking about it, show what actually happened. So yeah, I guess if you're following galactic astronomy, you might have heard that the early data release tree from the Gaia mission was released today. And anyway, so it's here are the contents. And maybe I can just like show this. As you see, like here, we're going 1.6 million years in the future. And the stars, individual stars, are shown. Oh no. Presumably shown as moving. I think my favorite ones are like the co-moving pairs. Oh my gosh, this is like, okay, let's just play it again. Once it's loaded. Okay, so you now see stars that become trails and I will send the link and you can look at it.
That sounds great.
At your own leisure.
It's a little bit lagging.
Yeah, it is a bit lagging. Anyway, it's a giant catalog of 2 billion stars, and there are some cool results already published by the Gaia team on the structure of the anticenter and also structures around the large and small Magellanic Clouds that you see over here. One also really cool result is that it's from the motions of like the apparent motions of quasars. They managed to, the Gaia team managed to measure the gravitational acceleration of the sun in the galaxy, which I thought was like pretty cool. And I don't think people expected this to be possible. And so with that, I'll just leave you with instructions to go check it out. And now let's hear from Gwen about what happened in the past.
Well, thank you. Yeah, so our first speaker today is Gwen Rudie. Gwen is an astronomer at the Carnegie observatories. Before that, you did your PhD at Caltech and got a bachelor's degree in New England at Dartmouth. And we're delighted to have you today. Gwen is an expert in wow, that's a hard word to say when you stumble over spectroscopy of quasars, but how we can use those spectra to probe everything in between. And today we're going to learn about the circumgalactic medium. So thank you so much. I think you're still
Can you hear me
muted.
now? Yeah,
yes.
Thanks. Sorry. I don't have control of my screen of Zoom when I have my screen share on.
So. Oh, no worries. And we'll give you like a 5-minute bell warning.
Okay, perfect. Well, thank you guys so much for having me. I'm delighted to be here virtually to tell you about work I've been doing with a number of collaborators studying the circumgalactic medium of cosmic noon era galaxies around a redshift of 2 to 3. So I always like to start with a statement that I believe we can all sort of agree with, which is that baryonic processes control sort of many of the observable properties of galaxies. So while dark matter may provide the scaffolding onto which galaxies are formed, we understand that the way in which galaxies accrete gas from the intergalactic medium will be critical to the way in which galaxy formation proceeds. In addition to that, how the energetic processes that occur when stars form and when stars die, we understand drive large-scale galactic winds, which again impact the forward evolution of these galaxies. And these processes are not actually particularly well understood. We believe, however, that these gas flows actually may play a very dramatic role in shaping and regulating galaxies. So in particular here, I'm just showing, given the time constraint of the talk, one example, which is the mass-metallicity relation in galaxies in the local universe from Andrews and Martini. And what we note is that as galaxies receive gas from the intergalactic medium, if it is lower metallicity than their ISM, this will, of course, dilute the metallicity of the next generation of stars that will be formed. And similarly, galactic winds, in particular, if they preferentially carry out the metals that have been formed in the most recent epoch of star formation, is also going to significantly impact the chemistry of the stars that form and therefore the full galaxy. And so understanding these sorts of processes is going to be very critical for understanding the forward evolution of galaxies. Now, I would argue that if we're interested in studying these processes, one of the best times in the history of the universe to do so would be around a redshift of 2 during sort of this cosmic peak of star formation, when the star formation rate density of the universe was highest. There's some theoretical work that would also project that that epoch is also sort of the cosmic peak of these gas flows. So here I'm just showing 2 sort of beautiful images that come out of some simulation work over the last decade that sort of illustrate 2 main phenomenon that I'll talk about at some length today. And so the first on the left is feedback, galactic winds that blow out, as I've said, potentially metals, but certainly ISM in general from these galaxies. And we observe in the spectra of high-redshift galaxies very prominent features from winds. And so we know that these are occurring in the distant universe very, very commonly. On the right, I'm instead showing work that focuses instead on how galaxies accrete gas from the intergalactic medium. And there's really been sort of a shift over the last 15 years or so in the discussion of how galaxies receive gas from the IGM, with a particular emphasis on the idea that at early times, like during these redshifts and previous to that, that galaxies may in fact be able to accrete gas relatively efficiently from the intergalactic medium in a relatively cold form, and therefore this may help to fuel star formation. But regardless of exactly how these processes proceed, one thing that I like to point out from beautiful images like this out of simulations is that if we are interested in studying these processes, we would do well not just to study the galaxies themselves, but also to study the gas that surrounds them in detail in the circumgalactic medium. So if we look off the plane of these galaxies, we might see direct evidence of the physical properties of gas in the CGM that might tie directly to these physical processes. So that's exactly what I'll tell you about today, work where we have taken very detailed spectra of distant quasars around a redshift of 3. We complement this with very dense galaxy redshift surveys, focusing on galaxies in the foreground of these quasars, where if one of the galaxies lies very close to the line of sight, we can probe the gas distribution surrounding this galaxy in very high detail using these quasar spectra. So just to touch on the galaxy and quasar survey that I'm talking about, this is the Keck Baryonic Structure Survey. It covers 15 fields across the sky with some of the brightest high redshift quasars accessible to Northern Hemisphere telescopes, such that the galaxies that lie in the foreground of these probe this sort of cosmic peak in star formation just above a redshift of 2. All of the spectra I'll tell you about today from of the quasars come from high-res and have really high signal to noise and high spectral resolution, which allow us to measure very precisely the column densities as well as widths of individual absorption systems, which tell us a lot about the physics of the gas in the CGM. I mentioned this is paired with a very large galaxy redshift survey, but today I'm not actually going to focus on most of that. I'm going to focus instead on the 8 galaxies, a very small sample, that lie within within 100 kiloparsecs of the line of sight to the quasar. And so we actually probe gas within the halo of these galaxies, within the virial radius of these galaxies, using the background quasar sightline. So just to touch on this sample a little bit more to give you some context for the types of galaxies I'll be discussing today. These galaxies are relatively luminous within about a factor of 3 of L star, these redshifts. They are relatively young, but with a wide range of ages, anywhere from sort of a dynamical timescale up to effectively the age of the universe at these redshifts. They have a wide range of star formation rates as well as stellar masses, and a clustering analysis performed by Ryan Trainer showed us that these galaxies sit in typical dark matter halos of about 10 to the 12 solar masses, which corresponds to a virial radius of about 90 physical kiloparsecs. So those are good numbers to keep in mind for scale. All right, so jumping right in, the high redshift circumgalactic medium, what does the CGM actually look like? Well, I'm a spectroscopist, so I will be showing you spectra during at least some portions of this talk. So what I'm showing here in black is the continuum normalized spectrum of this quasar, one of the quasars in our sample. And I'm showing this with respect to the redshift of one of the foreground galaxies that lies about 75 kiloparsecs, or roughly 3/4 of the virial radius, from the line of sight to this quasar. All of the colored curves show a full Voigt profile decomposition of the absorption in a variety of ionized metal features, from singly ionized silicon and carbon over here, triply ionized silicon and carbon, and 5 times ionized oxygen here. Now, there's 2 main points that I want you to take away from looking at these spectra. So the first is that the gas in the circumgalactic medium is extremely kinematically complex. So you can see that this is fit with a very large number of subcomponent Voigt profiles that represent individual structures in the gas or density inhomogeneities. And they span a relatively wide range in velocity, and you'll see later in the talk that they actually span a considerably wider range than what's shown here. But that overall, this is a relatively complex gaseous structure. The other point is that the gas is in fact multiphase. So if we look at these lower ionization lines traced by the singly and triply ionized species, these are actually fit with a very similar overall component structure where the centroid and widths of the lines are tied together. However, that structure is not at all represented in this oxygen-6 most ionized phase that we detect with these data. However, there is still considerable oxygen-6 gas at the same velocity, but with very, very different structure. What that tells us is, in fact, the gas within the circumgalactic medium is multiphase. And so we have evidence now that the CGM in high redshift is both multiphase and kinematically complex. What else can we learn from these data? So one thing we're lucky to be able to do is constrain the size scale of circumgalactic medium gas clouds. Now that's normally very, very challenging because with a single pencil beam survey, all you have access to is essentially these column densities. But we're fortunate that one of the quasars, one of our background quasars, is in fact gravitationally lensed. And what that provides is 2 images of this background quasar, which at the redshift of this galaxy are separated by only 400 parsecs. And so we can actually trace the very small scale structure of these ionized metals at this sort of 3/4 virial radius distance from this galaxy. All right, so what do we see when we look at that? All right, so what I'm going to do is replace the quasar spectrum that I've shown here with now the spectrum of the fainter image of this quasar, which is again 400 parsecs away. And what do we see? Well, overall, we see that the velocity scale of the absorption is roughly constant across these 2 lines of sight, 400 parsecs apart. So the overall structure that's causing this absorption appears to be larger in scale than 400 parsecs. The oxygen-6 is completely consistent across the 2 lines of sight, suggesting that these oxygen-6 structures are in fact larger than 400 parsecs. However, if we look at these individual little bumps and wiggles in these lower ionization state lines, what we see is in fact that the gas distribution there looks very, very different. So the individual structures that give rise to these individual subcomponents in the lower ionization gas have size scales much smaller than 400 parsecs on average. So overall, this is consistent with the idea that these lower ionization gas clouds may in fact be small clumps embedded in sort of a warmer volume filling medium that's traced in part by this oxygen-6 phase. And overall, that the structure that gives rise to all of this absorption appears to be larger than this 400 parsec scale. Now, the very small size of circumgalactic medium metal absorbers, I think, presents an enormous challenge for simulators, especially those interested in doing direct comparisons with observations. But I think that there's some novel approaches that have appeared in the literature that will be promising potentially for direct comparisons in the future. So here I'm just highlighting work from a handful of simulating groups. On the left, I'm showing work by Cameron Hummels, who has sort of pioneered work on sort of forcing high resolution all the way out to the virial radius of galaxies. And these enhanced halo resolution simulations can get down to relatively high resolution, even out at sort of the virial radius or half the virial radius. These aren't quite converged, but I think that there's some hope here for getting at these small scale structures. On the right two panels, I'm showing work by Drummond Fielding and Evan Schneider that have worked on idealized wind simulations. And you can see that in these simulations, they in fact do find extremely small structures of cool gas, in many cases precipitating out of a hot wind here in Evan Schneider's work. And that this might in fact be some of the types of metal absorbers that we're actually observing here. And so I think that there's some promising work that can come out of doing some direct comparisons, out of sort of future simulations in this vein. All right, moving on. What are the physical conditions of gas within the circumgalactic medium, and what does this tell us about accretion and outflows? So to study the physical conditions, what I'm going to rely on is the width of these individual absorption components, which encodes information about the gas temperature and non-thermal motions of the gas, which I'll call turbulence in this talk. So how does that work? Well, for an isothermal gas cloud, since the energy of different particles is effectively equivalent, what we expect is that the velocity distribution of ions of higher mass is overall narrower than that of things with lower mass, because the velocity should be inversely proportional to the square root of the mass of the ion. And so we expect, for instance, the silicon profiles to be narrower than the carbon profiles of the same ionization state. So I'm showing on the right-hand panel instances from the KBSS data where I believe you can see by eye that we detect overall the thermal broadening of this gas. The right-hand panel shows the opposite case where the bulk motions of the gas dominate. Here, the velocity structure is constant across mass. And so you expect, unlike mass elements, to show very similar velocity profiles, which is what's shown here on the right. Now, in practice, we don't look through these data by eye to measure temperatures. We fit them. And when we do that, this is the full temperature distribution that we pull out from the data where it is possible to fit the temperatures of these absorption systems. Now, this is not this distribution is not without observational bias. I just want to add that caveat from the beginning. In particular, we are not capable of tracing the majority of gas at high temperatures because the UV absorbers that we're using are not sensitive to gas at very high gas temperature. So what's notable is not necessarily where there is an absence of absorption, but rather that there is a very large amount of absorbers that are detected at intermediate gas temperatures. This is interesting for a variety of reasons. One is if you take sort of a very naive perspective of what gas in the CGM might look like, you might predict that you'd have gas at roughly the virial temperature, which is at 10 to the 6 Kelvin, this orange line, for these galaxies, or you might predict gas that's much closer to the typical intergalactic medium temperature, which is around 10 to the 4 Kelvin. We instead see most of the gas at this intermediate temperature. Fully half of the absorbers have these intermediate temperatures. The other reason this is interesting is that gas at that temperature cools extremely rapidly. It's at the peak of the cooling curve. And so in order for this gas to remain so prevalent, it requires either constant reheating or replenishment of this gas, which points to this idea that the high-redshift circumgalactic medium is dynamic and an excellent place to study the types of galactic physics I was talking about at the beginning of the talk. Now, I think that these temperature distributions are broadly consistent with this idea of cold accretion combined with gas heating or accretion shocks. But I think it will require more analysis to sort of get to the bottom of all of these things. Now, I told you in addition to temperature, we can also measure turbulent velocities. So this is showing now the turbulent velocity distribution for absorbers in the KBSS. Overall, the velocity scale of these internal motions within these clouds are relatively small. And if we cast that, to try and put it in perspective, if we cast that as now the total thermal energy internal to these clouds compared to the total internal energy, we see that the vast majority of absorbers are in fact dominated by the thermal energy contribution. With a little bit of algebra, we can recast this as the Mach number of the internal velocities within these clouds. And what we see is that these internal motions are almost always subsonic. So 80% of absorbers that have measured gas temperatures and turbulences show subsonic motions. This is in contrast potentially to the overall motion of the cloud through the circumgalactic medium, which you'll see later in my talk, can happen at quite high velocities. So overall, I think that this the physical state of the circumgalactic gas is showing good evidence for these heating processes that we think might be very interesting to study, and is broadly consistent with the general theoretical paradigm. But I think there's actually a lot left on the table in terms of doing more direct comparisons with theoretical work that would make predictions of the temperature distribution of gas in these halos. But if we want to sort of disentangle observationally absorbers that are heated by either outflow or accretion shocks, we would do well to study the kinematics as well as the chemical enrichment of that gas. So in the time that's remaining, I'm going to tell you a little bit about those kinematics. What can we detect inflows and outflows in the CGM, and what can the kinematics tell us about feedback? So for starters, I'm going to rely on redshift space distortions. So this is now showing the galaxy correlation function from the 2-degree field galaxy redshift survey, just to illustrate the idea. What we see here is the distribution of galaxies along the plane of the sky in the x direction. And in the y direction, we see the velocity distribution transposed into a distance. And we see two main anisotropies in this distribution, which gives us clues about velocity anisotropies that exist in the galaxy redshift plane. So the first is this elongation on small scales. This is due to the radial velocity of individual galaxies in galaxy groups that are sort of whipping about. The opposite is seen on large scales. We see an overall compression in the velocity scale. This is due to the coherent infall of galaxies due to the collapse of structure. All right, so now I'm going to show you the same thing, but with gas and galaxies. And I'm only going to show you one quartile of this distribution just to have higher signal to noise. So this is now the distribution of gas with respect to galaxies in that same plane. Hydrogen is shown on the left panels, and the right panels show for ionized metal species. And we see the same two distributions. So we see this finger of God anisotropy, which is due to outflows from these galaxies. And we see compression on large scales in the H1 and metal distribution, which we believe is due to the overall infall of this gas. So we can detect inflows and outflows on large scales across the CGM, and it appears to be common. Is there evidence that this is actually impacting the galaxies that are forming? So in some cases, we have evidence of spectacular examples. So this is an example of a 1,000 kilometer per second wind detected in absorption in a variety of metal species that has solar metallicity and also bears molecular gas. And I found the galaxy that we believe to be associated with this absorption system. It doesn't look that interesting in this infrared imaging where it was detected, but the spectrum shows us that's in fact a very broad line AGN that sits in the AGN part of the BPT diagram. And when we looked at its star formation rate, we saw that it was in fact had a significantly lower star formation rate than what we would expect for sort of the typical star formation for galaxies of its mass, characterized here by the main sequence of star formation at the redshift of this galaxy. So this is one example where we believe a wind has driven off a very substantial amount of the ISM, potentially bearing molecules as well, and this has impacted this galaxy. Now the question is, how common is this? Is this common across galaxies in the distant universe? And what we can say now is that, yes, I think it is. So here I'm showing the velocity distribution of individual absorption structures around all of the KBSS galaxies within this virial radius. So it's plotted now as a function of transverse distance on the sky and line of sight velocity in the y direction. And these are all, of course, the observed quantities without projection effects taken into account. So they're all lower limits on the 3-space velocity and 3-space distance of these absorption systems from galaxies. I'm comparing that now to the escape velocity profile for a dark matter halo that would host one of these galaxies. And what we can see definitively is that 70% of galaxies that have detected metal absorbers in the KBSS have unbound metals. So that's pretty exciting. What would these unbound metals, what more can we learn about them? So here I'm plotting them as a function of their ionization state, where the dark blue ones are the ones that are formally unbound. I'll remind you that things that are shaded just in this light blue, may in fact also be unbound depending on how the gas is projected. But these are all formally unbound from the system. What we see is that these are most commonly detected in high ionization metal lines, and they are not particularly commonly detected in high neutral hydrogen column density systems. Now, what that tells us is that it's likely that these absorption systems are either very highly ionized, very metal enriched, or both. And so they're very much consistent with what we'd expect for an outflow from these galaxies. And it's not a particularly small quantity of metals either. For the 5 galaxies that have unbound carbon-4, fully 20% of their carbon-4 column density is unbound. Now, if this gas is in fact due to an outflow from these galaxies, it represents metal-enriched material that would be permanently removed from the system. And so I think this is pointing exactly to that, the point I made at the beginning of how the chemistry of galaxies and subsequent star formation can be broadly impacted by feedback. All right, so what more can we do? How can we learn more? I'm currently working on modeling the ionization conditions within these clouds in order to measure metallicities and constrain masses for these individual absorption systems. I'm also very excited to connect this work with lower redshift work that I'm leading along with Xiaowen Chen and Sean Johnson in the Cosmic Ultraviolet Baryon Survey, or CUBS. This is a survey very much like the KBSS 15 quasars, now at a redshift of close to 1, observed with HST COS, where here, instead of tracing the cosmic peak of star formation, we're tracing the downturn of cosmic star formation. One other thing that I'm excited about that I think could really add perspective, especially to the kinematics of gas in the circumgalactic medium, would be new near-infrared observations. And I'm one of the project scientists for a new instrument concept called MIRMOS, the Magellan Infrared Multi-Object Spectrograph, which I wanted to tell you guys about since you all would have access to this instrument if it makes it to Magellan. The idea is full near-infrared coverage simultaneously for a relatively wide field of view in multi-object spectroscopy, or to have an integral field unit with a relatively, quite a sizable IFU size for an infrared, contiguous field for an infrared MOS. And in particular, that would be very exciting, I think, for the CGM work. So here I'm just showing a schematic of what we might be able to do in terms of morphokinematic analysis in optically thin circumgalactic medium emission lines, to be able to trace the kinematics of gas flowing in and out of these galaxies within the contiguous field of view of this exciting new spectrograph that we're hoping to fund for Magellan. And if we do so relatively soon, we would hope would be on the telescope by 2025. So that's all I have to tell you about today. I think I'm out of time, so I'm just going to leave my conclusions up. I did want to have one more note, which is that Carnegie is hiring staff scientists. So if you guys are interested in a role very similar to mine or have questions about it, I'd be delighted to answer them. The applications are due tomorrow, so you don't have a ton of time. But if you're interested in talking about that, I'd be delighted to tell you more about Carnegie and what these positions are all about. So I'll leave my conclusions up, and thank you guys so much for your time and attention.
Thank you. So this is really fascinating, and there are a lot of questions to ask, but I wondered if we could turn first to the molecular signatures in the outflows you were seeing in those molecule-rich winds. And so do you have insight into the temperatures of that molecular gas from those lines, or is it all sort of kinematic broadening at those lower temperatures? And could those be environments where you could sort of form stars in the outflows, is a question Avi is asking.
That's very interesting. So I'm not an expert actually in the analysis of the molecular gas. This was actually the very first detection of molecular carbon monoxide, et cetera, was this exact absorption system. And that was led by other authors. And it was detected in the early 2000s, in fact. So I have not actually analyzed directly the molecular gas in this system. I was interested in studying the circumgalactic medium of sort of more evolved red galaxies and happened upon the system.
Interesting.
Now, in terms of what the conditions in this gas are, the width of these lines does tell you something. The fact you can do actually detailed ionization analysis on the structure of the molecular species, the various molecular transitions that exist, and learn something about the temperature. The temperature has to be
the
relative
abundance of different
Yeah, of different transitions.
Species. Okay.
Yeah,
okay.
it gives you sort of a temperature sequence.
Understood.
I don't know the full details of this, but that is how it works. The gas does have to be relatively cold, otherwise this would disassociate. So
right.
The sort of intermediate temperature gas that we're talking about, that is likely things that would be traced over here, where we can't detect molecular gas out at these sort of 1,000 km/s locations. But here we're seeing very strong carbon-4 absorption, which is likely due to more ionized and also likely warmer gas. And you can see it goes, the detections here in metal species range over a very wide range of ionization state and plausibly gas temperature. So I hope that addresses at least some of the questions.
Definitely. And then I wondered if we could talk a little bit about sort of the pathway forward to compare to the simulation. So in this audience, there's a lot of people who run that sort of model,
Yes.
or if not exactly that sort of model, then something related. And I wondered if you could talk, I mean, questions that spring immediately to mind is this idea that you were posing that there's like very volume filling components versus like this cold gas has got to be tiny volumes, but lots of mass. And how do you, like, what do you imagine being the tracers that one could compare? If like, what are the, yeah, what are the quantities that one could get a hold of and what?
Sure. So I think the way that I like to work on this with simulating groups is that I like to take the observations a little bit past just the data itself to a little higher level of interpretation. So doing things like measuring these temperatures as opposed to just giving you guys raw line widths to work with. And I also like to, to the degree that it's possible, provide things like column densities and so forth. And I think what that means is that it's actually not that hard to meet halfway in between with simulators. So the challenge is I can't detect all gas, whereas you guys have detections of all your gas, obviously, in your simulations. You know where the gas that sits at 10 to the 6.5 or 10 to the 7 Kelvin, if it exists, is in these simulations. So I think doing something like asking for the gas that would be probed by, sort of singly ionized carbon through 3 times ionized carbon. So asking for those structures and then making a temperature distribution of that gas would be very interesting. One challenge though, so I did like sort of a cheap comparison of this with one of the fire simulations published by Zach Hafen. So he published the temperature distribution of gas in the halos of these fire galaxies. And one of the challenges with this comparison, though, is the KBSS, because I don't yet have masses, I'm working on this ionization correction. The KBSS distributions that I showed you, temperature distributions, are by number. So it's the number of absorbers. It's not a mass-weighted quantity.
Yep.
Whereas Zach's work is mass-weighted. It makes more sense for the theoretical community to report such things. And so I'm working on it from this direction, but I think with a little bit of sort of discussion with the theorists directly, we could actually probably come up with some pretty straightforward ways to look into the temperature distribution in these simulations in a way that's actually quite analogous to how it is analyzed in these data. And I'm actually really excited about doing that kind of work because I think we can learn quite a lot from each other. So
it seems like it.
Yeah.
And that's really exciting. When I see the richness of some of these spectral lines, and this comes back to a question that Anna was asking, which is when we're seeing substructure there, it seems like there's so much more information in those lines than just their equivalent width. And so do you think it's possible to like separately detect clumps that are moving at like kinematic offsets? Is that the substructure we're seeing, or is it different actually lines adding up to the sort of overall blended profile?
Yeah, so it's I think the way that I think about it, in particular this first example that I showed, so the sort of model that I have in my head, that I don't think we have perfect evidence that it is a unique model, but it's the one that I think makes the most sense, is that what we're actually doing is looking in this case through an outflow from one of these galaxies. The oxygen 6 is tracing sort of a warmer fluid that's likely more volume filling, might be the majority of like this outflow. So if you imagine, you know, some like river of relatively highly ionized gas coming out directly from the galaxy, and then out of that is precipitating these small gas clouds. And each one of these individual little clumps that you're seeing modeled as a single Voigt profile is now a significant different density contrast between this sort of more volume filling wind and a smaller parcel of gas that's probably cooled out of this hotter medium that's being thrown out of this galaxy. That's sort of what I carry around. But we know that not all CGM absorbers are that at these redshifts. So I could show you examples. I don't have them in this slide deck, but there are instances where we see very large column densities of neutral hydrogen gas that have almost no associated metals with them in terms of their kinematic alignment. Now, those are cases where I think that's a very likely absorption system that would represent one of these cold flows, because it's a very high H1 column density with very, very few associated metals, because we can detect metals, like pretty trace quantities of metals with these spectra, just because of the high quality of the data. And so, so you know, I've shown here, because I'm focused on the metal absorbers, instances where I think that actually what you're likely looking at is outflows from these galaxies, but we know actually that the gas traces more than that in these halos.
That's really amazing. Well, I think it's time for us to move on, but before we do, let's all thank Dr. Rudie again. This is amazing work, and I feel like this slide is a wonderful place to pause, because there's just such incredible richness in these data, and there's so much to learn, as you said. So thank you for the really exciting summary. There's a few more questions coming in on the Slack channel as we talked, then I had time to ask. So
perfect. Thank you so much.
Chime in there at any point. Thank you. Our second speaker today is Priya Natarajan. Priya is a professor of physics and astronomy at Yale University. So I was thinking about how to introduce Priya without spending the entire 20 minutes of your talk, Priya. And I thought that I could summarize some of your work as by the fact that you're an expert, I think, in kind of everything that you can't see in astrophysics, right? And you try to make these sort of traces of the unseen astrophysical constituents observable. So that's a hard thing to do. And without further ado, we're really grateful to have you here today.
Yeah. Thank you so much, Morgan and Anna, for inviting me. I have to say that this is not ideal to, I would have so much liked to be there in person, but, you know, as given how the pandemic has gone for me in terms of the sense of isolation, I'm just so grateful and thrilled to be even on Zoom. It's that bad, right? That some of us are excited even to be on Zoom. So I must confess that I was under the impression till yesterday that this was a normal ITC colloquium length. So I had a long, you know, the usual introduction and sort of weave into what I wanted to talk about. And so I have truncated it and to make sure that I share with you some really new, exciting results. So I'm going to focus really on a new result that we published a couple of months ago, and sort of the lead up to it, and explore the implications for this particular result. So what I'm really going to talk about is, many of you know. So first I want to say, I think that was an overkind introduction. Hey, so thanks, Morgan, for that. You know, many of you know that I've been working for quite a while now trying to use clusters of galaxies as laboratories to understand both what is powerful about them is that you can use them to study the properties of dark matter as well as dark energy. And so they are really sort of interesting laboratories. And gravitational lensing as a probe is particularly powerful as well, because it's achromatic, it's independent of the dynamical state of the object, which is relevant in this case because these are the most recently sort of actively assembling structures in the universe, very massive, and also the most efficient lenses. So that's the reason why we really want to use clusters to study. So first, I want to thank a lot of collaborators who over the years in this, as I said, this particular quest that I've been on trying to stress test cold dark matter models using substructure properties inside clusters. It has a long history. There have been lots of people there were many who were skeptical at the start that this could even be done, but there were many who were very supportive and who collaborated. Right now, I want to give a shout out to a couple of people. One is Massimo Meneghetti, with whom I've been working closely for several years, who has provided the expertise on simulations. Mathilde Jouzac, who is at Durham, and she has really helped in honing the lens mass modeling techniques and methods and the models that I'll be sharing with you today. I, of course, want to thank Lars. A lot of the early work in pushing through happened with comparisons with Illustris. So Anna Pilipic and Lars were really helpful. And I want to give a shout out to my former project student, Mila Chadayamuri, whose paper from a few years ago actually was where we saw the first hint of something very interesting that was really worth following up in terms of mismatches between predictions, theoretical predictions, and observational data. So just a quick summary to tell you why clusters are so interesting and important for the particular purpose of testing the nature of dark matter. As all of you know, one of the limitations and challenges of using astrophysical observations to nail down the particle nature of dark matter is the question of scales, right? So there's a real kind of what is accessible to us, both in terms of observations and simulations, right? So simulations have grown in sophistication greatly, but we are still not at the level. We are not actually modeling an individual dark matter particle. We are modeling aggregates of particles. But clusters, there are unique properties of clusters as observational sites in the universe, because they the mass, the overall baryonic mass in clusters is of the order of 10 to 12% at most. About 1% is in all the stars in the galaxies, and 10% is in the X-ray emitting hot gas, and the rest is all dark matter. And the reason this is interesting is because then the measured deflections, lensing deflections, are really going to be reflecting the detailed distribution of dark matter with greater fidelity than in most other objects, where this ratio might be tilted differently, for example, galaxies. And so the big questions that people have looked at for clusters is, what is the total mass? And as you all may know and may have heard the lore, clusters are also the objects that first provided the observational evidence for dark matter. So then there are deeper questions that you can ask about the connection between light and mass. In particular, how well light traces mass? And again, clusters are a very interesting place to probe this relationship. And of course, as I said, though we can't nail down the particle, we can really say quite a lot, as I'll show you today, about the nature of dark matter, just from the mapping the spatial distribution of dark matter. And not only are we able to now give you estimates of the total mass, integrated mass of objects, but we are now, I'll show you that we are able to derive the granularity of dark matter at a level where there's real convergence between the sophistication of what simulations offer today and observational data. So it's a very, very interesting, powerful moment when they are sort of better aligned. As I said, I've been trying to do this for more than a decade. And initially the data was not good enough for what I wanted to do, but then the simulations were not as good once the data got better. So there was a lack of alignment for a long time. But finally now, in the last 3-4 years, both the kinds of simulations and the variety of simulations and simulators, independent groups that are simulating clusters and providing predictions for substructure on small scales within clusters has grown. And the data has enormously improved because of the depth of HST data that's now available. So just as I said, I'm going to skip a lot of preliminaries. So if there are students who want to learn more, I'm happy to hang around and chat on Slack, or in our universe, when things get better, I am on sabbatical, and I was hoping to hang around, CFA and BHI. So you can catch me hopefully in person, right? In a few months, we have to be optimistic. So the interesting thing is that this is just a cute little schematic to drive home 2 points about gravitational lensing. As you all know, it's the deflection of light, distant sources. In this particular case, they're actually going to be galaxies deflected by foreground mass distributions. Here, I have a cartoon of a galaxy as a lens, intervening lens. But the case that I'm going to talk about is obviously clusters of galaxies. So you have a source here in between us and distant galaxies, and the total mass, integrated mass within the cylinder all the way from us to the source is what matters, the surface mass density enclosed. And there's a deflection angle, and this deflection angle that gives you an observable effect that we will see in a minute, that's measurable, is proportional to the total integrated mass in the cylinder, the projected mass in the cylinder. And the lines of sight to clusters, which are really rare objects, are pretty much dominated by that individual cluster. And it's also proportional, the strength of lensing, the efficiency is proportional to the ratio of angular diameter distances between us, the lens, and the source. And so interestingly, the underlying world models, so cosmological parameters, dark energy, et cetera, feed in this ratio of angular diameter distances. So obviously you can see that if the deflections are measurable directly from observations, then you can map the mass distribution knowing the underlying cosmology as a prior, or you can do vice versa. You can do one or the other. And if the data is good enough, we now have enough statistical techniques to actually try to do both simultaneously. Right. So constrain, for example, dark matter and dark energy. But in what I'm going to talk to you about today, we are going to take the underlying cosmological model as a prior. So omega lambda, et cetera, are going to be put in by hand, and the Hubble constant. And we're going to be really fiddling around with the mass distribution and what we can derive, what detailed properties we can derive that will enable comparison, direct comparison with cosmological simulations, in this particular case of the lambda CDM model. So this is just to give you another sort of a quick view of what we are really trying to do when you get the observational data. So what you really see, the way lensing manifests. So you see the first image, Abel 370, where you see this blue arc you can see in the top left-hand corner. And so that's a highly distorted image of a distant background galaxy that lies behind this foreground cluster. You can see all the cluster members in those little fuzzy yellow dots. Those are cluster galaxies. And so in the schematic, you can see now I'm giving you a more sort of realistic cartoon where I'm showing you that there could be blobs of dark matter. So subhalos that are associated, as we'll see in a minute, we will make that association with light, with cluster locations of cluster galaxies. And so what lensing really allows you to do is to map from the observed image plane, sort of these distorted shapes, superposed distorted shapes, on the lens, which is cluster galaxies, and the overall BCG and so on in the lens. And there are these multiple regimes in terms of a mapping. If you think of it as a mapping from the image plane to the source plane, it's not a simple mapping, it's a nonlinear mapping, because there's a region, a strong lensing region, where an individual background source lining up just behind the mass distribution could get multiply imaged, magnified and multiply imaged. So that's a highly nonlinear regime. Then as you go out, as you move to less exquisite alignment, you have weak systematic distortion in shape. So that's sort of a linear regime. And a lot of the mass modeling building that we do combines the data, the observations from these. And of course, there's an in-between mesoscale regime where you have both a little bit of magnification and stretching and distortion of shape. So these are all now part and parcel of the information we extract from the observations and include in the creation of this lens model. And so there are codes that we use, standard codes, and the one that I'll be showing you that we have used to construct the lens models is a very old one that I was part of developing way back when. It's of course extremely, it's evolved since then, and it's called Lens Tool. It's a publicly available software. So once again, and in the little sort of animation that I'm showing you, it's just to show you the range of observed geometries for strong lensing that you are likely to get and give you a feel. So what you see there in fuzzy pink, sort of two shaded pink regions, are two large-scale clumps of dark matter. And the systematic lensing effect on a set of sources, circular sources, all of them are circular. And what you are seeing in the distortions are the lensing effects in the two regimes, this multiple imaging strong regime, the meso regime, and the weak regime at the outskirts of this image. So these are the observed features that you include in the modeling. And all you need to remember for the purposes of this talk are that these two regimes are characterized by very different observational manifestations. And we now know how to delineate them because we have data, we can confirm spectroscopically all these multiple images, multiple image sources, and many multiple families of multiple image sources. And so these are very important tight constraints in the modeling. So let me show you now, give you a feel for what it is that the mapping permits you to do. So as I said, you have this image plane where you see these observed, highly distorted multiple image sources, and you have a mass distribution, a gravitational potential. And you see on the, when you map it back to the source plane, what you see is this diamond shape region is the caustic. This is the region behind which, as I said, you have this exquisite alignment of a source shown now as a circular source in red, blue, when it's inside that region. This caustic marks the region where the magnification or the amplification of a background source diverges. It goes to infinity. In reality, it just becomes very, very large. And so once you cross, you know that you cross this caustic when the image geometries change dramatically. So the red corresponds to the red multiple images that you see, and so on and so forth. So this area of the caustic, right, this region enclosed within the caustic is a measure of the ability of a gravitational potential to strongly lens a background source. So I want you to make a note of that because we're going to come back to that property a little later on. So let's move now to Lambda CDM. So, there have been many tests of Lambda CDM, as you all know. It's a spectacularly successful model, but it's precisely because it's so spectacularly successful that we need to really do precision tests and stress test it. And so there's one very interesting, robust prediction of cold dark matter. There are many, including density profiles, etc. I'm going to focus on one today, and that is the properties of the subhalos, collapsed subhalos that inhabit larger scale halos. In this particular case, cluster scale halos and the substructure inside cluster scale halos. So about 10 to the 15 solar mass cluster scale halos, and substructure down to about 10 to the 9 solar masses, as we'll see. And so the prediction, the robust prediction from CDM is that this slope of this mass function, subhalo mass function, is minus 1.8. And I want to visually also show you that this is a very clear-cut prediction in CDM, and it's fundamentally different if you change the nature of the dark matter particles. So on the right-hand side of this panel, you see a warm dark matter simulation of the same cluster at the same time, the same initial conditions except for warm dark matter. And you see that the substructure has been smoothed out in warm dark matter compared to cold dark matter. So it's very tantalizing, as I said, right? Astrophysics wise, we feel very challenged that we cannot get down to the nature of the dark matter particle. But so here you can see there's a real sharp difference. And so if I can tabulate and add up all the substructure, if I can map the substructure somehow and count it up, then I can really test whether there is agreement with cold dark matter models or not. So quickly, to just show you conceptually, to do this precisely conceptually, during my PhD years, I realized that we need to build a model that is particularly attuned to comparison of observational data with simulations, with what cosmological simulations are doing, right? What providing in terms of data. And to find analogs, to literally to do mock observations of the simulation and to do detailed comparisons. So the premise here is that you think of the complicated, complex gravitational potential of a cluster partitioned into two scales, largely speaking, two large scales. So one is a large scale smooth distribution of dark matter. It's a sum of potentials that are smoother and a sum of perturbers. And these perturbers, we associate them, small scale perturbers, with the locations of individual cluster galaxies. So, this game has been done. I've been doing this. There are many other workers, people who've been groups around the world who have adopted this framework, but have independent implementations. We know these lens models are quite robust. We are able to characterize the errors, the degeneracy. So this is like a well-trodden path. So, and roughly what we are doing is we are constructing these models that I show you here for Abel 2218, and we produce maps of the substructure distribution. So the granular dark matter distribution show you as peaks and valleys, right? So we are able to do that. And to do that, I told you that we had to make one assumption of how to relate the location of the subhalos with light, sources of light in the cluster, that is cluster galaxies. So frequently we have adopted self-similar parametric models to model these subhalos. And we've used various models, NFW, pseudo-isothermal elliptical mass distributions, isothermal spheres, et cetera, et cetera. The only key thing to remember is that that the parametric models, it's very well supported that these kind of work. And I can talk about it later, how we know that these work and so on. The key thing here is that we exploit what this allows you to do. This particular way of attaching light to mass allows you to use empirically observed relations for cluster galaxies. So the Faber-Jackson law, for example, helps you relate the mass to the light in individual cluster galaxies. So we adopt that framework. In the work that I'm going to show you, we are actually, the data is good enough that we can leave that index free. We do not have to assume that the central velocity dispersion of a model subhalo scales as 1/4 to the luminosity scaled in terms of L star. Okay, so let me quickly now tell you about other small scale problems. So, obviously you probably realize there is a small scale problem that I'm going to talk about. So that's the big reveal here, right? So there have been other problems that have been pointed out in CDM. One of them was the cusp-core problem. So that's the internal structure of halos. And here we are talking about the shape of the density profile inside 1 kpc or so. And so it's predicted, CDM predicts that, the slope should be a power law slope, the density profile. And what is found, especially with low mass dwarf galaxies and so on, that there is evidence for a turnover and therefore a core. So this problem was claimed as a huge crisis for CDM, but it was resolved. So I'm not going to spend much time on it because I really want to get to the new problem that I'm getting. So I want you to remember here, this is a problem on kiloparsec scales, where you can imagine that refinements in the resolution of simulations could go to resolve this. And indeed, feedback and improving ingredients that go into the simulations and being able to find fainter dwarfs where you can make those measurements resolve the issue, right? Then there's another small scale problem. This is now we are talking not on individual galaxy scales, but rather sort of groupish scales, which is the missing satellites problem. And this, again, you have all heard a ton about, and we know that there was a paucity of, there is a paucity of detected. So the observational, the real universe does not give you as many satellites as CDM predicts, right? So again, this has sort of been resolved. This is not something that is a nail in the coffin of CDM, okay? So let me now come back to tell you about this new problem that has revealed, which I think is much more serious, therefore interesting and intriguing. So first of all, quickly to show you, this lens mapping technique allows you to map subhalos and the subhalo mass function inside clusters. So in red, you see, this is previous work that we did with the Millennium simulation. So the black histogram is the Millennium simulation, and the red histogram is derived from lensing data. So you can see, by and large, the x-axis, right, is quite remarkable. Completely independent techniques. The abundance of subhalos, we don't have a problem on cluster scales. We don't have the analog of a missing satellite problem. We actually have the right number of subhalos, right? And so now with an improved simulations, this is work that was done in 2017, and with Illustris, and with a brand new data set with deepest images of clusters, Abel 2744, that was part of the Hubble Frontiers fields. Once again, we find that the abundance is not an issue. So we don't have a problem like the missing satellites problem on this scale in CDM. But we actually found another issue, I think, I missed that slide, which is now, because the models were good enough, we could actually plot the radial distribution of substructure. And that did not match. So that was the first clue that there was, even though we can match the abundance, it's very obvious that somehow the internal structure of subhalos does not match. Okay. And so you can see the mismatch in the radial distribution of subhalos. The red histogram, once again, is Abel 2744. I mean, these are obviously, cases. These are special cases. These are extreme lenses and so on. As you'll see, I'll enlarge the sample and do the analysis and show you what we find. So what we did now is said, okay, we've got to look more deeply with better models. So we used 20, clusters chosen from the CLASH program, which is a shallow look program, and the deep frontier fields. And then we followed up with data from MUSE. So we have spectroscopic redshifts for almost all the multiply imaged families that we can recognize and associate with each other, as you saw in those geometries that are now familiar, and cluster membership. So we did as good a job as we possibly can. So we built the best possible mass models, including kinematic data, measured velocity, central velocity dispersions for cluster galaxies. We first tested our models, and then we realized the models were very robust, and now we actually incorporate them as priors, okay? So then what is a new diagnostic? Now that you have such a great mass model, what can you do? How can you push it further? As we saw earlier, those critical curves, what we can do is we can look at a lens mass model and sort of an observed lens, and look at a mass matched analog in a simulation and map the area of these caustics provided by small scale structure. And the small scale structure I'm talking about here, right, in this context, is not sub-kiloparsec. We're talking about 5 kpc, 5 to 10 kpc scale, because that's the scale on which we are actually sensitive to picking up strong lensing by individual cluster galaxies on top of the overall cluster. Okay, so this new metric is the galaxy strong lensing probability. It is just a sum of all the little caustics that you have that are produced by all the little clumps of subhalos, and that is scaled by the overall area of the smooth components caustic. And this, of course, depends, as you can imagine, on the source redshift, depends on the redshift of the source. So here is from one of the best mass models that we have for a cluster. Here is the probability, GGSL probability for this cluster. And this is giving you a feel of all the uncertainties in the models and the things that we can tweak in the models. And you can see it nicely tanks off. Okay, this is great. So how does this compare with CDM simulations? So what we get from CDM simulations is the orange curve. So there's an order of magnitude discrepancy. And so we can think of many possible ways in which you might be able to resolve this. Maybe, the clusters are not as representative of all clusters, clusters that we are finding as lenses are extreme and so on. And it turns out that, after enormous investigation of all possibilities, this persists. What this is telling you is that the inner regions of cluster galaxies are significantly more concentrated in the real universe than simulations suggest. So there are a couple of other diagnostics. So there's one interesting clue that we see, that we can see that where simulations are probably falling short or are wanting is, as I said, in this internal structure of the subhalos. And that you can see immediately when you look at the circular velocity of substructure inside simulated clusters. Those are all the dots, and the black is what we get from the lensing model. So that's the gap that we see. And so I'll quickly move to the conclusions. So, so we just had a science paper out in September, and we had like 52 pages of supplementary material where we looked at each one of these possibilities. So I'm not going to spend time. I'm just going to tell you that all the obvious things we have looked at, and we have arrived at, so you just now have 2 possibilities, right? And they're both incredibly interesting, intriguing, and important. And so first is that either there is some missing piece in terms of the interplay between dark matter and baryons in cluster regions, in particularly in these high density regions. And I'm saying that because I already showed you that this is not related. In fact, it goes in the opposite direction to all the other crises and mismatches of small scale in CDM. And the other possibility, of course, and we have to be open-minded, is that there could be deeper problems with the assumed nature of dark matter itself. So, I mean, and, I don't want to speculate too much. We're very cautious that it's one or the other. And, and I tend to think that the problem is likely that we're missing a component in the simulations, partly because, as I showed you, that we can see that the properties of cluster galaxies are not quite as reproduced as well as we would like. So anyway, I'll just stop here and open up for questions. Thank you so much.
Thank you, Priya. So Avi had a question which related to one of the 2 points you just put up. So maybe you want to go ahead and ask yourself.
Well, first of all, I wanted to say happy birthday, Priya.
Thank you. Thank you so much. Yeah.
So obviously, I mean, the one Achilles heel of any inference about the nature, I mean, this could mean something about the nature of dark matter, but the question is whether the baryons make a difference, and especially in the course of galaxies where we know there are other issues. So do you think that the simulations are sufficiently reliable in terms of the baryonic physics for us to consider this as any indication about the nature of the dark matter?
Yeah, no, that's a great question. And thanks, Avi, for the birthday wishes. So as I said, right, so what we are finding, this statistic is sensitive to the mass enclosed within a few arc seconds. So around a few arc seconds. So the Einstein radii of individual subhalos. So that corresponds to about 5 to 10 kpc. And so that is the mass, that implicates the mass well outside the light. So this is the integrated mass within that region. So, we are a lot less sensitive in detail to the baryonic processes, except one of the things that we did try is we looked at simulations in which we artificially turned off AGN feedback, which is tuned to be quite strong in clusters, and which causes the rearrangement of mass on very large scales inside cluster galaxies. And we found that, yes, then this gap does shrink a little bit. You can't, no one process or set of processes could bridge this order of magnitude gap. So, but you do need feedback for many other, to match many other observables in clusters, like the overall, census of baryons and so on. You need feedback. So I think what is intriguing about this particular discrepancy, the scale, I mean, it is small scale, but it's not as small scale as the other problems. And this is also a small scale where issues, we believe, of resolution and the interplay with baryons are not going to be the only part of the solution. We believe that they can't be, only because of the scale. So because, if you actually look at 5 to 10 kpc of around a cluster galaxy, it's well outside the light. So this aperture size, I think, is kind of intriguing. So one of the things that we are doing, right? So in terms of simulations, it's clear that there's a lot of dynamical processing and transformation when galaxies fall into clusters. And there have been many questions raised about whether, our prescriptions for tidal stripping and dynamical friction, whether they really are accurately implemented. And there's this issue of numerical artifact of over stripping of tidal stripping. But we found that cannot account again for an order of magnitude. But I think in future work, what we want to do is to see, another way to separate out whether it's overall large scale dynamics in the cluster is that we are going to extend these lens models. They were just in the core. So there is HST data in a project that I'm involved in called Buffalo, which will allow us to map the data out to the virial radius. Then we can radially bin, even if it's just 2 radial bins, we can look at the contribution to this cross-section from 2 radial bins and look at regions where, the inner regions are where you expect a lot of processing to have happened for these cluster galaxies. And in the outer regions, because of the crossing time, those are not guys that could have made many, many passages and been affected as much. So we think we should be able to sift out a lot of these issues. And also, my NSF proposal recently was to also look across various kinds of simulations, which, as you pointed out, that implement the subgrid physics in fundamentally different ways, to see if that, could be a possible source. Yeah, no, I am not, I am not want to jump to an alternative dark matter model. But, in the interest of the preservation, intellectual preservation, it's just that, it just opens up, more work. We're not going to run out of things to imagine, speculate, and have fun with. So I think one thing that, one avenue that we are exploring there that I'm particularly interested in is that, all the self-interacting dark matter does not go in the right way as it is proposed. It would have to be tweaked in order to explain this. So as I said, none of the solutions that were proposed to explain the other small scale problems they're actually going to make it worse for this problem. So nothing that is currently available works like out of the package. There's a little bit of room to play. So one room to play are potential dark matter models where the self-interaction cross-section does not depend on velocity, but depends directly on the density. That is different. And I think that's one thing that we are trying to play with to see if it can give us something.
It's really fascinating. Along those lines, Julian Munoz had a question. Do you want to just pick up and ask yourself, Julian?
Yeah, sure. It's about this last tension you showed us, which is very interesting. Can we confirm that the subhalos are denser rather than there are more than we expect? Can we distinguish these two hypotheses?
Yeah, because I told you that the numbers match, right? So the overall numbers, so we don't have a problem. We don't have a counting problem. So we can reproduce the numbers, but what we are not able to reproduce is the internal structure, because this metric is designed exactly for that. And, so we have a paper that will come out very soon, which has been submitted, in which we are doing, using another metric. And I think that also very clearly shows that what is really off is the internal structure of the subhalo. And that is, doing sort of a power spectrum analysis and looking, which, as a function of scale, then you can say something about the compare simulations and the observational maps. Yeah, so I think it's very clear that that's what is happening. And I think the reason we want to keep the room open for, the dynamical processing is that, we know that, the masses of subhalos do change dramatically after tidal stripping. You can lose quite a lot of mass, and principally dark matter in the cluster environment. Yeah, you lose stars, you spill out a few stars and you spill out gas and so on, but you lose a lot of the dark matter content of the subhalo. So that's why, it's probably something to do with the dynamics. I mean, I don't know, there are many other kind of crazy things that happen, right? So for example, I'm not pushing this idea, okay, by any means, but just because your question is so interesting, that, if you run the simulation forward in time, then you find something very interesting. So if so right now I'm comparing like with like. So I've compared a lensing cluster at redshift 0.3 with simulated analogs at a redshift 0.3. But if I actually, because we're talking about the internal structure and internal density structure of subhalos, if I then try to compare with a cluster of the same mass matched at either an earlier epoch or a later epoch, then I'm seeing something quite interesting, which is why I think, we are missing something in the internal structure and the dynamical processing.
That's great. Thank you for the answer. I look forward to seeing this appear.
Yeah, well, thanks, Julian.
So Priya, do you think that there's like an observational counterpart to that? Like, could one make a map this detailed of a higher redshift cluster and ask if, like, is it feasible to repeat this experiment?
Right,
essentially with different lenses?
Right. The whole problem, I think the problem with lensing, as I said, while the lensing itself is independent of the dynamical state of the cluster, the actual dynamics is actually quite complex, right? So
yeah.
At higher redshift, even if I find a mass analog, it will not be the right dynamical analog to something at a different redshift. So, okay. So to be consistent, you really do have to run the clock, down to the same time. Except that, you see, because the problem is that the subhalos in the real universe are more concentrated and they're more efficient, strong lenses, then the question is, we know when structure assembles, how the the internal density structure actually changes, right? So one can try playing with the clock in the simulation, but you can't really do it in the real universe. But it'll tell you something. Again, I think the point is that, if simulations are suspect, we really want to see whether, as Avi asked, whether it's the feedback or whether, as Julian mentioned, whether it's the dynamics. You want to separate out what in the simulations we are getting wrong. What we could be getting. We all know that probably tidal stripping and dynamical friction, we know we are not getting wrong. We are not getting right. We know that from another problem that a lot of us, many people on this call also work on, which mergers of black holes and so on. When we look at the last parsec problem, this, that, and the other, when we look at, there's something kind of missing in our picture. Because black holes should merge much more easily, and we think that's why gas is implicated and so on and so forth. But it's clear that our simulations are really not quite there in terms of modeling many of these important processes.
Interesting. Can I ask you to take maybe 1 or 2 minutes and reflect on, I think something that came through really clearly in your lecture was that all of this work has kind of defined a methodology, and you're thinking about new tracers and so, I imagine it taking, this so many years to do this for this one cluster, but really you're kind of like setting up a way to do this. So what happens if we repeat this? And you made a good argument for why clusters are a favorable place to do this, but what if we do this on a smaller scale? So like, when I've heard some conversation about like lensing of stars by like galaxies halos. So could we like go further down that mass distribution? What do you think there's something to be learned there by looking for substructure on a like galactic halo level? And how do you think one would proceed?
Yeah, no, that's a great question in terms of like the future directions. And I wanted to show this plot. So notice the x-axis here. I've been showing you subhalo mass, right? So one clear prediction of CDM is that this ratio of substructure to parent halo mass, right? So I could make the same plot for the Milky Way. And I could, that is work that we are doing right now, which is to try, the only problem is that, the mass measurements, how you measure the mass and what that mass is for the substructure in the case of lower mass halos is not as well defined. So it's a trickier comparison to make, but CDM is very clear, right? Because if what we have found is a problem that is endemic in CDM, then it should show up in smaller scales. So, I recently saw that, Jenny Green and collaborators have tried to do this. I think Karsten is the name of the first author of that paper. I think he's a student at Princeton. And they tried to do a very similar analysis, and they found that the radial distribution of substructure for Milky Way scale halos, exactly the same problem, that they tried to do. And what they are able to, what they can claim, the problem is when you have one object, right? So by the way, the results that I showed you here are for an ensemble of 11 clusters. So it's not one tweaked by one peculiar object, right? So, the problem with having one object in which you are able to make observational measurements and then extrapolate from that is tricky, because and what they find is that if you populate back the radial positions of the so-called orphan halos, right? And the ones that get artificially tidally stripped, if you put them back in, then you can match the radial distribution better. So I told you that in the case of clusters, right, that we do not have, because of the scales involved, there are no halos that are completely disrupted that we have access to. So you may remember that we have access to, this technique with the best, deepest HST data can take us down to about 10 to the 9. Pushing even one order of magnitude down in the subhalo mass is extremely difficult. It's in the next, we can do this maybe statistically. We won't be able to do it this kind of individual modeling like we've been able to do here. In the future with Roman and JW, there are sort of possibilities of doing things more statistically and maybe extending this lower mass cutoff. But if you look at 10 to the 15 is the mass of the overall cluster, and this is 10 to the 9, right? So the analog that you would want to do in this plot, so that's 10 to the -6. So that, remember, if you go for a Milky Way type halo, right, that is a 10 to the 6 solar mass clump. That is still not quite, with all the nice stuff that Anna and others are doing, looking at streams and other signatures, we're not quite there to get a full census. You may be able to say, oh, there's one subhalo there that punched through and we are seeing the signature. But the kind of work that we're doing, we're saying this population of that mass, we still don't have that. And from the modeling of individual galaxy lenses, people like Simona Vighetti and others have been showing, and I think Cora Dworkin is also doing work along those lines now, which is trying, they are once again able to say that, looking at these multiple images on galaxy scales, they say, well, I think maybe there is a 10 to the 6 or 10 to the 7 solar mass halo, one of them that should be placed roughly at that location to reproduce the images better. So I think we don't yet have, the sort of the kind of census you would like that we have on cluster scale yet. But I think that is, that's a very interesting and promising direction to go forward. And especially, I think there are surveys, upcoming surveys where, the Saga survey and so on, where you will have many Milky Way level galaxies for which you may have, substructure mapping possible, satellite mapping. So we might be able to say something then. But I think at the moment, it's worth exploring whether there is a replication of this kind of problem on other scales.
Well, I think that we should stop there for the moment and thank both of our speakers. I know that Gwen had to log out, but thank you again, Priya.
Yeah, thank you very much. Yeah, thanks everyone. Stay safe and have a wonderful and safe holiday season.
That's right. And so I think we will resume this particular forum in about a month. And in the meantime, everyone, stay safe, as Priya said.
Yeah, bye.
Bye. Thank you so much.
You're welcome.
Thanks, Anna and Morgan, for putting this together.
Thank you all.
Wonderful.
Wow. So that was quite a number of people stayed around for it was pretty cool to say.
Yeah,